This last segment goes into more detail on transport through pores. Um, we're going to look at this. We're going to kind of gloss over a whole bunch of it and kind of get down to a final few little things and not dig too much into the details, right? But the model assumes something about membranes, and this is a pretty common uh, when we look at membranes and how they work. Pores are actually extremely important. It's not so much diffusion through the membrane usually as it is pores and pores controlling how things go through. So you've got a pore radius, you got a pore number in circular pores per unit area, you got a membrane thickness. Pores, the pore and the fluid are electrically neutral, right? So no electrical forces are considered in this. Complex mixing on both sides of the pore, complete mixing on both sides of the pore. So flow within the liquid on either side can be neglected. It's in steady state, um, and the pores are enough so that bulk flow can be calculated by continuum hydrodynamics. Okay, so and what does that mean? The pores aren't the size of the molecules, right? And so you can get through the pores in a more fluid way. Kind of think about the planetarium dome. The planetarium dome at Delta State has lots of pores in it, and you don't even notice them when you're at night, and they're there just to make the dome lighter. Actually, it's all they're there for. We got some things on the left. You know, when you think about flow from left to right, that's our convention here. We got our total pressure, we got our solute concentration, we got our osmotic pressure of things that can't go through, or osmotic pressure of solutes. Sigma pi, the things that can't go through, 1 minus sigma pi, plus the water pressure, things that can go through. In the pore, we've got some concentration that's a function of your travel distance along the pore. We got our concentration on the right. We have our pressure in the pore that's some function of your distance in the pore, and we got our pressure on the left, on the right. All right, so left, right, in the pore. As always, like volume transport, we're looking at viscous flow through a tube, which we looked at in chapter 3. And so when you look at what viscous flow through a tube looks like, it becomes clear that this coefficient LP is this calculable, right? Calculable quantity based on physical characteristics of the pore and the viscosity of the fluid and the number of pores per unit area, right? So radius of the pore, length of the pore, viscosity of the fluid, number of pores per unit area. Um, and so volume flow is exactly what we had before. We just now know more about, when we think about it in this actual physical context, we know more about it this way. This is the difference between as I talked about earlier, the phenomenal, Lord, I can't speak this morning. Phenomenology, where we're just trying to describe what we see, and a more detailed, let's look at the physical characteristics of what's going on and build up from there to a better understanding of what's happening in the pore. And so this is a volume flow we got to before, right? We got a difference in concentration of the solute. We've got the reflection coefficient. We got the difference in pressure from one side to the other. All of this you've seen before, right? And if we look, if we look within a single pore, we get exactly what we expect out of viscous flow through a tube, right? Okay. If we look at solute transport, and we have to keep in mind when solute transport takes place, that you can't, the solute has some size, and so the whole pore is not available to it, right? And so the solute has to be within some volume of the pore. And so the that some subvolume of the pore. And so let's look at this through a single pore. They go through all the calculations. You come up with this nice, pretty little function, F. It's a function of the size of the solute particle and the pore size. And so for a membrane, the solute flow, right, is this reflection, average solute concentration times the volume flow, and then your diffusion piece for the solute that depends on the difference in solute concentration. And you get, after going through all of this, that 1 minus sigma, this reflection coefficient we were talking about, is this function f, right? That the reflection depends on, or the ability to pass through it, depends on the relative size, and this makes complete sense, the relative size of the solute versus the pore size, right? So if the solute's bigger than the pore, it's clearly not going to go through. It's only when the solute is smaller than the pore that it's going to go through. And the smaller it is, the easier it's going to be for it to pass through the pore. Uh, so this is going at it in this last section, I think section 9 in the text, is going at it from more fundamentals. Can we work back to the phenomenology that we had in the earlier chapters? And so in summary, we've got our volume transport, we got our volume solute transport, our hydraulic permeability, our solute permeability. We've got a characteristic diffusion length, and this characteristic diffusion length depends on the exact properties of, it depends on the size of the pore, the solute permeability, the flow rate. It depends on all these things, the reflection coefficient, right? It gives us a characteristic length for this. Um, and then this average concentration, they go into more detail. The average concentration is this term that you would expect, which is just the linear combination of the two concentration on either side divided by 2. And this other term, if you want to look up what g of x is, you can. G of x depends on the details of the characteristics length, right? And it takes into account that the diffusion length, it kind of gives you a scale for the pore and gives you a different profile than just linear through the pore, right? Um, and so this takes into account the fact it's a factor that corrects, it's a correction factor, if you will, for just the standard average to say, well, you know, if this assumes that if you start off at CS and you go in a straight line to CS prime, that's what this piece right here does. This is a correction factor for the fact that depending on your characteristic length, it may look more like this, or it may look more like that, right? And so it's just a correction factor to take into account that this may, oh, look at that. This may not be exactly a straight line. Um, and that's it for this chapter. All right. Hopefully we can get into the problems, and a lot of this will make a lot more sense and kind of um, help you get a better understanding of volume and solute transport. Talk to you soon.